Right. So uh, right. So I welcome you all for today's EMF session. Thank you for your patient waiting. Due to power cut, the class has been delayed. Anyhow, once again I welcome you all. In my last class, I have discussed about field due to a circular loop, right? Magnetic field due to a circular loop, right? So let me recollect the things which we have learned in our last class. So let us consider a circular loop on XY plane, right? Circular loop on XY plane with its center at the origin as shown in figure, and the radius of the circular loop is rho. And magnetic field is determined at a point P, right? Magnetic field is determined at a point P, 0, H. To determine magnetic field at a point P, let us consider a differential length dl, right? Differential length dl at x, y, 0, right? X, y, 0. Because the circle is considered on xy plane, z component is 0, so x, y is 0. And the current is flowing in anti-clockwise direction as shown in figure. In other words, in pi direction, right? In pi direction, the current is flowing. So therefore, dl is equal to rho d pi a pi bar. And from equation 1, substituting dl, ar bar, and r values, and simplifying, we will get magnetic field, right? So r is the distance between point P, that is 0, H, and x, y, 0, right? So find out the distance, vector distance, and scalar distance, substitute, and simplify, we'll get the answer, right? So this is the answer. H bar is equal to I rho square by 2 rho square plus H square power 3 by 2 Az bar. So Az bar is the direction of the magnetic field, right? And I have also drawn the magnetic flux lines with respect to circular loop, right? So as shown, so these are the magnetic flux lines. So I have drawn the magnetic flux lines by using right hand thumb rule. If you hold the circular loop in your hand, and the thumb will shows you the direction of the current, and the remaining fingers will gives you the direction of magnetic field lines as shown in figure, right? So if the current is flowing in anti-clockwise direction, the direction of magnetic field is z as shown, right? So that is what we have discussed in our last class, right? Let me do a small problem related to this. It's a very simple problem, and is required in fact. A circular loop located on x square plus y square is equal to 9, and z is equal to 0, carries a direct current of 10 amperes along a pi bar. Determine magnetic field at 0, 0, 4 and 0, 0, minus 4. So this is the problem, right? A circular loop is given. So x square plus y square is equal to 3 square, right? 9 in the sense 3 square, right? So therefore rho is equal to 3, right? Rho is equal to 3. Radius of the circle is 3, and z is equal to 0. That means the circle is on xy plane. As we have discussed earlier, the circle is on xy plane, right? So magnetic field due to a circular loop, magnetic field due to a circular loop is given by I rho square by 2 rho square plus h square power 3 by 2 az bar, right? So here rho is 3, and current is also given. I is equal to 10 ampere current, and a bit, right? A bit at 0, 0, 4, right? At 0, 0, 4. So in this, what is the point P? At what point we have calculated? At 0, 0 h, right? At this point, at 0, 0 h, right? On z-axis we have calculated, right? That means 0, 0 h, right? So therefore here 0, 0, 4, right? 0, 0, 4 means what? Means what? H is equal to 4, right? H is equal to 4, right? So therefore all the values are known, right? And hence substituting all the values, I is 10 into rho square is 9 divided by 2 into rho square is 9 plus h square is 16 power 3 by 2 az bar, right? So this you will get, right? So if you simplify this, you will get 0.36 az bar amperes per meter, right? So this you will get, right? And b bar is equal to sorry, b bit at 0, 0, minus 4, right? That is h is equal to minus 4, right? B bit 0, 0, minus 4. So therefore h is equal to minus 4, right? So if you substitute h is equal to minus 4, what you will get? Magnetic field h bar is equal to 0.36 az bar a amperes per meter. The same answer you will get. Why h square, right? In the formula we have h square, right? So therefore it may be positive or negative, you will get the same answer, right? It may be positive or negative, you will get the same answer. So therefore magnetic field does not depend on, right? From this problem we can conclude that magnetic field magnetic field due to a circular loop does not depend on the point considered, right? The point considered, right? So therefore direction of magnetic field, right? Direction of magnetic field due to circular loop does not depend on the point considered, right? So the point of interest may be anywhere on z-axis. It may be on positive z-axis, or it may be on a negative z-axis, irrespective of the point where we are calculating magnetic field. You'll get magnetic field same, right? So here you can see in both the cases. So in both the cases, you can see this is AZ bar, direction of magnetic field is AZ bar, and here also direction of magnetic field is AZ bar, right? So therefore, the direction of magnetic field does not depends on the point, right? Then it depends on what? The direction of magnetic field depends on what? The direction of magnetic field depends on the direction of the current, right? The direction of the current, right? So for example, this is the circular loop, right? And let us say this is z-axis, right? And the current is flowing in this direction, anti-clockwise direction. When the current is flowing in anti-clockwise direction, the direction of magnetic field is this, right? So this is the current direction, current direction, and this is field direction, right? Magnetic field direction. On the other hand, if this is the circular loop, right? This is the circular loop, and this is the z-axis, right? If the current is flowing in this direction, right? If the current is flowing in this direction, right? So previously it is anti-clockwise direction, and now it is in clockwise direction. Then the direction of magnetic field is this one. So this is the direction of magnetic field. Direction of magnetic field, right? So therefore, direction of magnetic field depends on the direction of current, right? It depends on the direction of current, right? So this is about magnetic field due to a circular loop, right? So therefore, the direction of magnetic field is z, right? For this case, right? When circular loop is considered on xy plane, the direction of magnetic field is z, right? So that is the reason why in this derivation, right, we have neglected the second term, this term, right? We have neglected this term, right? That means arrow bar. The field in row direction is neglected, right? Because the magnetic field is in z direction. So therefore, magnetic field in all other directions is negligible. That is the reason why I have neglected this one, right? So let us move on to another new topic. Ampere's circuit law, right? Ampere's circuit law, right? So this is similar to Gauss law, right? In electrostatic fields, we have discussed Gauss law. In electrostatic fields, we have discussed Coulomb's law and then Gauss law. And similarly here in magnetostatic fields, we have discussed Biot-Savart's law and now Ampere's circuit law, right? So coming to Ampere's circuit law, Ampere's circuit law states that, I will give you the statement first. Ampere's circuit law states that the magnetic field the magnetic field, sorry, oh, just a minute, the power is gone. I will be back in a minute. Right. Right. So welcome back. Ampere circular law states that the line integral of magnetic field line integral of magnetic field about a closed loop is equal to the direct current enclosed by that loop, right? So this is Ampere circular law, right? So Ampere circular law states that the line integral of magnetic field about a closed loop, and that closed loop is called as Amperian loop, right? Let me recollect Gauss law. What is Gauss law? Gauss law is the total flux passing through any imaginary surface, right? The total flux passing through any imaginary surface is equal to the total charge on that surface, right? The total charge on that surface, that is xi is equal to q, right? Xi is equal to q, right? So and that means what? Surface integral d bar dot ds is equal to q, right? So this is what we have discussed earlier, right, in Gauss law. So similarly here, Ampere circuit law, the integral of magnetic field about a closed loop is equal to the direct current enclosed by that loop, right? So that means integral h dot dl is equal to I, right? Integral line integral h dot dl is equal to I, right? And this is called Ampere's circuit law. So line integral of magnetic field, right? Line integral of magnetic field is equal to the direct current enclosed by that loop, right? The direct current enclosed by that loop, right? Or the direct current passing through that loop. So that is Ampere's circuit law, right? So we know that I is equal to surface integral j dot ds, right? In chapter 1 we have discussed current and current density. In the topic I have discussed I is equal to surface integral j dot ds, right? So therefore equation 1 becomes, right? Equation 1 becomes line integral h bar dot dl is equal to surface integral j bar dot ds, right? Let us say this is equation 2, and applying Stokes theorem, on left hand side of equation 2, right? Applying Stokes theorem on left hand side of equation 2. What is Stokes theorem? Stokes theorem will give the relationship between line integral and surface integral, right? So that means line integral can be converted into surface integral, or surface integral can be converted into line integral. That is Stokes theorem. And what is divergence theorem? Divergence theorem is the relationship between surface integral and volume integral. Surface integral can be converted into volume integral, or vice versa, right? So therefore, applying Stokes theorem to the left hand side of equation 2, we will get line integral of h dot dl is equal to surface integral of curl of h bar, right, ds is equal to surface integral j dot ds, right? And similarly here also, the magnetic field is uniform, right? Field is uniform, right? So therefore h bar delta cross h bar and j, right? So they are uniform, so therefore they can be taken outside the integration. And we have then we have left with surface integral ds on left hand side and surface integral ds on right hand side. So therefore the above equation will become del cross h bar is equal to j, right? Del cross h bar is equal to j, right? So this is Ampere circuital law and Maxwell's equation, right? Maxwell's equation for magnetostatics, right? Maxwell's equation for magnetostatics, right? So earlier we have discussed Gauss law, and that is also Maxwell's equation for electrostatics, right? And this is Ampere circuital law, and this is also Maxwell's equation for magnetostatics, right? And let us say this is equation 3. Equation 2 is the integral form, and equation 3 is the differential form, right? Differential form or point form, right? So this is about Ampere circuital law, right? So um, earlier also we have defined what is that del cross E is equal to 0, right? So this is one Maxwell's equation. Then for electrostatic fields, del cross E is equal to 0, and del dot D is equal to rho v, right? So these are the two Maxwell's equations for electrostatic fields, right? So these are the two Maxwell's equations for electrostatics, right? For electrostatics, and del cross h bar is equal to j, and one more equation we will derive later, right? So this is the third. Let us say this is the first Maxwell's equation, and this is the second Maxwell's equation, and this is the third Maxwell's equation, and fourth Maxwell's equation we will discuss later, right? So here what I'm going to tell you is curl of E or del cross right, right? So here what I'm going to tell you is del cross E is equal to 0, del cross J, so del cross H is not equal to 0, right? Del cross E is equal to 0, del cross H is not equal to 0, right? So curl, dot product and cross product. How you define dot product and cross product? So one difference is dot product means open, cross product means closed, right? Dot product means open, cross product means closed, right? So that means if you want to understand more clearly, if you take a line charge, so this is the line charge, right? What is the direction of electric field? This is the direction of electric field, right? Normal to the line charge everywhere it is normal to the line charge, right? That means diverging away from the line charge, right? Diverging away from the line charge, and those flux lines are not closed, right? Those flux lines are not closed, but whereas magnetic flux lines are closed, right? Magnetic flux lines are closed. So here I have drawn the magnetic flux lines, right? So here if you observe, the magnetic flux lines are closed, right? Magnetic flux lines are closed, right? So therefore curl of magnetic field is not zero because they are closed. Curl in the sense closed, right? So magnetic flux lines are closed, so therefore del cross H is not equal to zero. Electric flux lines are not closed, so therefore curl of E is zero, right? Curl of E is zero. So that is how we can understand, right? So this is Ampere circuit law, and let us move on to the applications of Ampere's circuit law, right? Applications of Ampere's circuit law, right? Earlier we have seen applications of Gauss law, right? So here we are looking at the applications of Ampere's circuit law. Just a minute. Right? Infinite line current, right? Infinite line current, right? So that means magnetic field due to infinite line current, right? Earlier we have seen, right? Let me go back. Magnetic field due to a straight wire, right? So this is the expression for magnetic field due to a straight wire finite in length, and this is the magnetic field due to a straight wire infinite in length, right? So that means H bar is equal to I by 2 pi rho A pi bar, right? I by 2 pi rho A pi bar. So infinite line current, magnetic field due to infinite line current, H bar is equal to I by 2 pi rho A pi bar, right? So this is the mathematical expression for magnetic field due to infinite line current, right? Infinite line current. The same equation I'm going to derive using Ampere circuit law, right? So using Ampere circuit law is very simple procedure, right? So let us say x-axis, y-axis, and z-axis, right? So let us consider an infinite line charge along z-axis, right? An infinite line charge, along z-axis, right? Let us consider an infinite line charge. So this is an infinite line charge along z-axis, and which carries a current I, right? Which carries a current I, right? So to determine magnetic field, right? Let us assume, let us assume an infinite line current along z-axis carrying a current I as shown, right, as shown in, right, and assume Amperian path, right, assume Amperian path to determine magnetic field, right? Amperian path, what is meant by Amperian path? It is just like a Gaussian surface, right? Imaginary Gaussian surface. Similarly here also imaginary Amperian path, imaginary Amperian closed loop, in other words, right? So therefore, to determine magnetic field due to an infinite line current, let us assume an Amperian path, right? Amperian closed loop, right? So this is an Amperian closed loop, circular loop, right? Amperian closed loop, um, whose radius is rho, right? Whose radius is rho, and um, in pi direction, right? So this is pi, right? And it is moving in pi direction, right? So this is called the Amperian path, Amperian path, right? So this is Amperian path, right? So to determine magnetic field, let us consider a differential element, right? Let us consider a differential element dl, right? Let us consider a differential element dl, right? So where dl is equal to rho d pi a pi bar, right? Rho d pi a pi bar. So this is dl, right? So now from Ampere circuit law, right? From Ampere circuit law, from Ampere's circuit law, line integral of h dot dl is equal to I, right? Line integral of h dot dl is equal to I, right? And um, this can be written as integral 0 to 2 pi h bar dot dl. What is dl? dl is rho d pi a pi bar, right? dl is rho d pi a pi bar. Earlier I have explained to you, right? So let me take you there, here, right? dl, right? So dl in Cartesian coordinate system and dl in cylindrical coordinate system, right? So this is the dl in cylindrical coordinate system, right? So in dl in cylindrical coordinate system, or here I have forgotten to tell you, you can write in a general form, dl is equal to h1 du au bar plus h2 dv av bar plus h3 dw aw bar, right? So this is the um, um, uh, general form. You can remember this one, right? So because you know what is h1, h2, h3, and what is uvw, right? So those values you know, right? So from this shortcut method, by substituting h1, h2, h3, uvw, you can get whatever the form you want, right? So for Cartesian coordinate system, h1 is equal to 1, h2 is equal to rho, h3 is equal to 1, and u is equal to rho, v is equal to pi, and w is equal to z, right? That's it, right? So substituting all those values, you'll get this one, right? And um, the differential element is taken along pi direction, right? Is taken along pi direction, right? Just like this here in this figure, it was shown, right? Dl is in pi direction, so therefore only pi component is considered, right? So here also I did the same, right? So dl is in pi direction, right? So this is pi direction, like this. So this is pi direction, pi direction. So therefore dl is considered only pi component, right? So therefore dl here, right? So dl is replaced with rho d pi a pi bar, right? And this is equal to I, right? And here also, to apply Ampere circular law, the condition is field should be uniform, right? There also in Gaussian law also, to apply Gauss law, what are the conditions? Field should be uniform, and field should be normal to the surface, right? So those are the two conditions to apply Gauss law. And similarly here, to apply Ampere circular law, field should be uniform, right? Field should be uniform, right? So therefore when field is uniform, h can be taken outside, right? H can be taken outside, and rho is a constant, right? So therefore 0 to 2 pi d pi a pi bar is equal to I, right? So integral of d pi, so what is integral of d pi? Is pi, right? So substitute pi limits. So h pi rho into 2 pi a pi bar, and which is equal to I. So therefore h bar is equal to I by 2 pi rho a pi bar, right? So this is the magnetic field due to a long wire, right? So using Ampere circular law, right? So using Ampere circular law, I have derived the same equation. Using Biot-Savart's law, earlier we have seen, right? So using Biot-Savart's law, so this one, so this is using Biot-Savart's law. I have determined magnetic field. See the procedure here, how lengthy is the procedure. So a lot of so many steps, right? I have written here, so many steps I have written, right? So after so many steps and following some assumptions, you will get finally this equation, right? But whereas using Ampere circular law, not more than 4 to 5 steps, right? This one, right? So using Ampere circular law, within 4 steps or 5 steps, I have obtained the expression magnetic field due to a long straight wire, right? So that is about applications of Ampere's circuital law, right? And Let us move on to another topic, magnetic flux density. Magnetic flux density, right? So another magnetic flux density, right? So yet another important topic, magnetic flux density, right? So earlier we have discussed electric flux density. Let's see, for every topic I'm discussing in magnetostatic fields, I'm comparing with electrostatics, right? So there, this we have discussed, and here we are discussing this. Like that, I'm comparing with electrostatics. So therefore, if you are well aware with electrostatic fields, then it becomes easy to follow magnetostatics, right? So whatever the topics we have discussed in electrostatic fields, with respect to electrostatic fields, the same topics are replicating here, right? The same topics are replicating here, right? So therefore, electrostatic fields are very, very important, right? So in electrostatic fields, we have discussed electric flux density, right? Electric flux density. So what is electric flux density? Um, electric flux density is d bar, right? D bar is equal to epsilon naught E bar, right? D bar is equal to epsilon naught E bar, right? So magnetic flux density is similar, is similar to electric flux density, right? So magnetic flux density is denoted as B bar, right? So magnetic flux density is also a vector B bar, which is equal to mu naught H bar, right? B bar is equal to mu naught H bar, right? So just I have compared with electrostatic fields, and I have defined magnetic flux density. B bar is equal to mu naught H bar, right? And Webers per meter square, right? Webers per meter square, right? And where mu naught is permeability, right? Permeability. Mu naught is permeability. Epsilon naught, earlier we have defined epsilon naught. Epsilon naught is permittivity, right? Permittivity or dielectric constant in free space, right? So similarly, mu naught is permeability, and mu naught is equal to 4 pi into 10 power minus 7, right? Mu naught is equal to 4 pi into 10 power minus 7 henries per meter, right? So earlier we have defined epsilon naught, which is equal to 10 power minus 9 by 36 pi, right? Farads per meter. This one is farads per meter, farads, right? So that is the reason why we have discussed capacitor, right? In electrostatic fields, and in magnetostatic fields, we will discuss inductor, right? Henries per meter. So mu naught 4 pi into 10 power minus 7, and epsilon naught is that value. So you have to remember those values, right? So similarly, in electrostatic fields, we have magnetic electric flux density, magnetic flux density, electric flux, magnetic flux, electric flux. So what is electric flux? Xi, right? Electric flux xi, and which is equal to surface integral d bar dot ds, right? So this one is electric flux, right? Electric flux. So similarly, here magnetic flux, magnetic flux, right? So magnetic flux is pi, capital pi, which is equal to surface integral b bar dot ds, right? Webers, right? B bar dot magnetic flux Webers, magnetic flux density Webers per meter square, right? So this is magnetic flux density, right? And one more thing here, in electrostatic field, the flux passing through a closed surface is same as the charge enclosed, right? So the electric flux passing through any imaginary surface is equal to the total charge enclosed, right? The total charge enclosed, right? So but here the total flux passing through any closed path, or magnetic flux passing through any closed path is zero, right? So there previously in electrostatic fields, the total flux passing through any closed surface is equal to q, but whereas here the total magnetic flux passing through any closed surface is equal to 0, right? So that means surface integral over a closed a closed integral, right? So surface integral is equal to 0, right? Surface integral over a closed path. So this one is a closed path, right? Closed path. So therefore, closed integral b bar dot ds is equal to 0. That means the total flux passing through a closed path is 0, right? A closed path is 0. Why? Because magnetic flux lines are closed upon themselves, right? Magnetic flux lines are closed upon themselves, right? So for example, if we consider a magnet, right? If we consider a magnet which has north pole and south pole, right? Magnet, if you consider a magnet which has north pole and south pole, and draw the flux lines, right? So we can draw the flux lines like this. The flux lines will flow from north pole to south pole, leaves at north pole and enters at the south pole, right? Similarly, here leaves at north pole, enters at south pole, right? And these flux lines go on like this, go on, right? And leaves here, right? Leaves here and enters here, right? They will enter here, right? They will enter here, right? So therefore, if you consider, right, if you consider a closed path, if you consider a closed path, right, if you consider a closed path, what happens? The total flux entering or passing through again they will entering, right? Flux passing through the closed loop and again entering, right? We have considered a closed loop. The flux lines are entering and again closing, entering and closing. So therefore, what is the total flux? Is zero, right? Total flux is zero, right? Let me consider the electrostatic fields, right? Line charge. So this is the line charge, and the electric flux lines are like this, right? So these are the electric flux lines due to a line charge, right? So they are not closed upon themselves, right? They are not closed upon themselves, right? So therefore, if you consider, right, if you consider a closed path, right, if you consider a closed path, so here the flux lines are leaving, right, through the surface. So through the surface, the flux lines are leaving, right? The flux lines are leaving. If you consider a closed surface, the flux lines are passing through the, right, passing through, and they are not returning back, right? If they return back, the total flux will become zero, right? So therefore, in electrostatic fields, the flux lines are not closed, and whereas in magnetostatic fields, the flux lines are closed. So therefore, the total flux over a closed path is zero, right? Over a closed path is zero, right? I hope you understood, right? So therefore, the total flux passing through a closed path is zero, right? Is zero as indicated in equation 1, right? And now, from divergence theorem, from divergence theorem, as we know that the divergence theorem will give the relationship between surface integral and volume integral, right? So therefore, surface integral of any function is equal to volume integral of divergence of that function, right, is equal to 0, right, is equal to 0, right? So therefore, we can write delta dot b bar is equal to 0, right, because field is uniform, right? Field is uniform. Delta dot b can be taken outside the integration, and we will have delta dot b bar is equal to 0, right? So therefore, this is equation 2, and this equation, this equation is called Maxwell's equation, right? So one of the Maxwell's equation for magnetostatics, right? Equation 1 is the integral form, and equation 2 is the differential form, right? Equation 1 is the integral form, and equation 2 is the differential form, right? So this is the second Maxwell's equation for magnetostatic fields, right? So with this, we have completed 4 Maxwell's equations for static fields together: electrostatic fields, 2 Maxwell's equations, and magnetostatic fields, 2 Maxwell's equations. Total 4 Maxwell's equations we have defined, right? So let me summarize the Maxwell's equations, right? Let me summarize the Maxwell's equations. Static fields. Differential form, integral form, and remarks. Right? So serial number 1, here differential form, delta cross E bar is equal to 0, right? Delta cross E bar is equal to 0. Integral form, line integral E bar dot dl is equal to 0. Right? And second one, delta dot d bar is equal to rho v, surface integral d bar dot ds is equal to volume integral rho v dv. Okay, so this is nothing but Gauss law. And third one, third Maxwell's equation, here delta cross h bar is equal to j line integral h bar dot dl is equal to surface integral over a closed surface integral j dot ds. And fourth one, delta dot b bar is equal to 0, right? And surface integral b bar dot ds is equal to 0, right? And this is Ampere's circuit law, and this one is non-existence of magnetic monopole, right? Non-existence of magnetic monopole. And this one is conservativeness of electrostatic fields, right? So these are the four Maxwell's equations which we have defined so far with respect to static fields, right? So very, very important Maxwell's equations, right? So in examination, they will ask you to derive this. So conservativeness of electrostatic fields in the sense one, the energy spent, for example, if you throw a ball, right? If you throw a ball upward direction, the energy spent will be given back when ball is returned. That is called as conservativeness of electric field, right? And conservativeness of energy, right? And that applicable to electrostatic fields, right? And non-existence of magnetic monopole. Fourth one is non-existence of magnetic monopole, right? Means what? We have a magnet NS, right, which is having a north pole and south pole. If you break magnet into two pieces, right, if you break magnet into two pieces, again these two pieces having north pole and south pole, and this is having north pole and south pole, right? So therefore you cannot separate north pole and south pole in a magnet, right? So therefore non-existence of a magnetic monopole, right? Mono in the sense single pole is not available, is not exists, does not exist, right? So therefore the that means what? Flux lines are closed. If we can separate north pole and south pole, we can have isolated flux lines like electrostatic fields. As we cannot separate north pole and south pole, the flux lines are always closed, right? Are always closed upon themselves. When flux lines, magnetic flux lines are closed upon themselves, then total magnetic field around a closed path will become zero. That means surface integral b bar dot ds is equal to 0, right? That will become 0, right? So this is about Maxwell's equations for static fields, right? So with this I will close the class, and we will continue in the next class, right? So thank you very much for your patient listening. Just a minute.